After that, we'll get into section 8.3, which we'll talk about in a bit. I'm not going to say anything about it yet. Does anyone remember anything about secant and cosecant? Now there's like a full weekend between when we talked about it last and now. Anything. Anything. I'll take anything. Yes?
The range is negative.
No.
Maybe.
That's tangent.
Wait, what did you say?
Oh, I guess, let me do this. Okay, so let me talk about tangents, and then we'll talk about the inverse stuff, because I thought we did talk about cosecant and secant. No?
Yeah.
Did we do a graph that looked like this?
Yeah.
Yes?
Yeah.
Okay, so let me go back to Desmos. Back to Desmos. So if I graph sine, there it is. Look at that. Ooh. Where will cosecant have asymptotes? Where sine is 0. Yeah, so there should be an asymptote here, there, infinite.
Yeah, it flips and goes there.
Also, when sine gets 1, 1 over 1 is 1. But when sine gets smaller, 1 divided by smaller than 1 is bigger than 1.
Yeah.
So I expect it to kind of go like that, and then there's going to be an asymptote there, so it's going to look like a bunch of repeated parabolas. Over here, the outputs are negative, so it's going to be a negative parabola, yes? So if I look at it, when we graphed it last time, but if I make Desmos do it, and if I use the mouse, okay, look. The mouse that's alive. Here, there, sit there. If I turn on cosecant, bam, there's the cups. If I zoom in a bit, that's more like what your picture is going to look like. Yes? So there's the asymptotes we're talking about. There's an asymptote here, and it goes up because 1 over less than 1 is bigger than 1. So that graph is one of the funkier looking graphs you've ever seen, especially if I turn sine off. Turn sine off and just let cosecant sit by itself. That's just weird. Yes? That looks like an overhead view of very long tables that I'm trying to seat people. Seating chart time. Long ass table. So anyway, what would be different with secant? The shape of secant would be the same, but what would be different? The location of the
Shifting?
asymptotes, because cosine is 0 at different locations than sine. It's actually kind of like, huh? Yes, exactly. So since cosine is sine shifted back 90 degrees, secant is cosecant shifted back 90 degrees. Yes, I like it. So if I graph here, let me make this become secant. Turn him on. There you go. He's been shifted back by 90 degrees. Yes?
Yeah.
Okay, that only makes sense because secant is related to cosine. Cosecant is related to sine. Okay. And that really looks tricky now. It's like you need 3D glasses. Alright, is everybody with me so far? Now, okay. I don't know why past Jeff did this, but from what you've told me, I did talk about secant and cosecant, but I really didn't talk about tangent?
We graphed tangent, but we didn't do cotangent or anything.
Oh, so we talked about tangent. Now, can somebody tell me anything about tangent? Anything. I'll leave the floor. I'll leave it open. What can anyone tell me about the graph of tangent? It's a very slight curve. I love it. It looks like it wants to be. Okay, cool. But considering there is a curve, what does it look like it wants to be? Cubish.
Yeah.
I know it's not cubish because it has walls, and polynomials don't have walls. They can go everywhere. But they have walls and it repeats, but it's definitely very different from sine and cosine, which only makes sense. Because it's the quotient, it's the division of sine and cosine. It should look a little freaky. And to be honest, it doesn't look as freaky as you might think. So tangent, can somebody tell me where the first wall is for an unshifted tangent? Because what's on the bottom of tangent? What's tangent? What over what? Sine over cosine. So what's on the bottom of tangent? Cosine. Where will there be a wall? What axis will cosine be 0 on? Cosine loves x. Y-axis. So a 90, negative 90, all the odd multiples of 90 degrees. Pi over 2. You with me? So, since cosine is 0 at negative pi over 2 and pi over 2, what happens there for tangent? What would I put here considering the bottom of tangent is 0 there? Asymptotes. Can't be here, can't be here. Pretend like that's in the right place. Okay. Let me stop for a minute. Is everybody still with me at all? Assuming you were ever with me. Okay. So the walls have to be there because the bottom of the function is 0 at this point. So we know we have to put a wall when that happens. We've seen that before. And then in the middle, we've already discussed this. The number out here is not the true amplitude because there is no ceiling and floor, but it does tell me where it is at this intermediate step. First place there's a wall. One step in, it hits this. The next step in, it hits 0. The next step in, it hits that. And the next step, it hits the wall. It doesn't hit it, but it approaches it. And then we got, oh yeah, I made that great discovery. That's just so exciting. There we go. The curve is so slight, it's kind of nerve-wracking. If I just made the scale better, then it would look better. Okay, it'll be right. Are you guys, we talked about that last time.
Yeah.
So let's talk about, now what's the period of tangent before I get too far?
Pi.
Why is it pi? Yeah, it starts at negative pi over 2 and it ends at pi over 2 and then it repeats. So how long did it take for it to make one complete cycle? Pi. Half a pi, whole pi. Okay, I still haven't applied a pi. I'm gonna apply pi. Make a pi, that'd be even better. So if I give you, for example, this. Yeah, sure. I'm pretty sure I made a big deal out of this. And I do apologize. The nice thing for me is we're about to get into, we do chapter 10 before my other class does chapter 10, so I won't be overlapping anymore, but we're still kind of overlapping. So that's why I keep asking if I've said something to you yet. What would I do here? What's the 3 tell me? Yeah, what did I say? The quote, unquote amplitude, right? It's not a true amplitude because it go past it, but it does tell me the first step in and the third step in where I go. So now instead of going to negative 1 and 1, I'm going to go to negative 3 and 3 at the first step in the third step. Yes? So are you still with me? Okay. Am I recording? Oh, yes, I am. That's very useful. So the amplitude, quote unquote, is 3. How do I figure out the new period?
Factor.
Yeah, I could. That'll help me get the phase shift, right? How do I factor out a 2? I have to factor a 2 out, so how do I do that? I'll put that there.
Minus pi.
Good, because when I take a number out, I divide it out. Pi divided by 2 is that. What's my k? K is 2. So what was my original period?
Pi.
So I take the original period, divided by k. There's my new period. What's my step size?
Half.
How many steps do we take? 1, 2, 3, 4.
Pi.
So it'll be pi over 2 divided by 4. Pi over 2 times 1/4, pi over 8. So what I want you to do is eventually make it a one-step deal. If pi is being cut in half and I have to cut that in fourths, now I'm cutting it in eighths. I'm just cutting it into smaller pieces. So if I divide multiple times, I multiply everything I'm dividing by to accumulate how many cuts I'm making. Okay, maybe. And last little thing that Trent helped, what's the phase shift? Not really the last thing because you can see it, right? What is it? You see it, right? What is it?
Right. Pi.
Thank you. Okay, right. Pi over 2. Okay. Now, I made a big deal out of this. What's the one thing that's sort of optional for sine cosine that is imperative for tangent?
The cycle begin and
Beginning and end.
cycle.
And I have no idea if you really understand why. But it's because I have negative pi over 2, pi over 2. If I compress it or stretch it, it actually moves it. When I started at 0, that part didn't change, because if I multiply 0 by anything, it stays 0. But now, if I compress it, it's like it moved, and then I phase shift and it moves again. So it is very difficult to track that movement. When I do the beginning and end, it algebraically does that for me, which kicks all the jazz. The only thing you have to remember is all of this, plus when does tangent start? When the inside is no. That's the whole problem. When does tangent start? When the input is negative pi over 2, yes? That's what we've chosen. We've chosen to graph this. So when the input is negative pi over 2, that's where the first wall is going to be. And when does it end? It never ends. No, stop. Actually, that's true. It never does end. Okay. So we did all this last time. We did the tangent stuff. We talked about it. I showed you the period was pi, all this kind of business, yes. And if I, help me out. If I add pi to negative half of pi, what do I get?
Pi.
Yeah, half of pi. Divide by 2, I get pi over 4. If I add pi to half of pi,
Halves pi.
and then divide by 2, how far is this?
Pi.
No.
No.
What's 3 pi over 4 minus pi over 4? What's 3 pi over 4 minus pi over 4?
Half pi.
2 pi over 4, which is pi over 2, which is the new period there. Right? So you can always double check. When I did sine and cosine, beginning and end were optional because the phase shift told me where it would start. What was our phase shift?
Right.
And where did we start?
Pi over 4.
So why am I not starting at positive pi over 2? Because it didn't start at 0 before, and I also compressed it. Poor little dude. And then to graph this, where do I put the walls? Shaka, when the walls fell. Where do I put the walls? Where's the first wall for the cycle we're graphing?
Pi over 4.
Yes, it begins at pi over 4. How much do I step by?
Half of pi.
No, pi over 8. So this will be 2 pi over 8, 3 pi over 8, 4 pi over 8, 5 pi over 8, 6 pi over 8, which is 3 pi over 4, which is where we predicted we would end. This is where we predicted we would end. Okay. Wall at the beginning, wall at the end. I am now going to go up to 3, down to negative 3 because of this dude. So the first step takes me here, and that's when I hit the amplitude, then 0, then the positive, and then the wall. So I go shabunga, and I go shabunga. That was pretty good. You guys have experienced how horribly I write and draw. So if I draw anything semi-good, it's like it's time to celebrate. Okay. So listen, I still calculated the new period the same way. It's the original period divided by k. That never changes. It's just that for tangent, the original period is 5. Now what do you think about cotangent?
Probably the same.
The period's got to be the same. Because cotangent is just 1 over tangent. They're very much related. But if I want to, let's graph cotangent real quick. Can somebody tell me what's on the bottom of cotangent? If I rewrite it. No. Yes. But in terms of sine and cosine.
Oh, it's
Sine over cosine.
Yes, no, that's tangent. What's cotangent? Cosine over
At
sine.
the bottom of. Yeah. Well, because it's 1 over a tangent, so and tangent is sine over
You
cosine.
don't, yeah. Okay. So what's tangent?
Sine.
Sine over cosine. Cotangent is the flip of that.
Yeah.
So it's be cosine over
So
sine.
it would be-
When is sine 0?
It's 1.
What's the sine like? Which axis is the sine like? The y-axis. So what is it not like? The x-axis. What angles are kind of like define the x-axis?
90.
That's there. What's this?
0.
0.
Pi.
Pi. 2 pi. I could also go negative pi. Yes?
Yes.
Okay. I can't really. It's can only bend so much. So again, so in the background of this, we know this is this. Where will the walls be? They'll be whenever sine is 0. Sine is 0 at multiples of pi. So we get to pick. This entire time we've been picking which picture to draw and go, it repeats forever, leave me alone. So we just draw one complete cycle and we're like, that just repeats, leave me alone. Copy and stamp, copy and paste, leave me alone. So cotangent, where will there be walls? We pick 0 and pi. We like to be close to 0 and we like to be positive if we can. Tangent, we want to stick close to 0, so we decided to go negative pi over 2, pi over 2. That was the choice we made. There are an infinite number of these guys that we could have picked. We picked that one. So for cotangent, we're going to pick, what does that say, Jeff? Oh, it's just my asymptote, okay. 0 to pi. And it's going to, now here's what's different though. Can somebody please tell me, what is the cotangent of pi over 4? What's the cotangent of pi over 4? What side of pi over 4? Square root of 2 over 2. Yes. Now listen real quick. I don't know if you're all being extra shy today. Dear God, you can't forget these. This isn't, oh, that was on the last step. This is forever and ever and ever. Everybody you take after me will assume you know this. So the cosine of pi over 4 is rad 2 over 2. What's the sine of pi over 4? That's the one angle where they are
The same.
the same. So what's the sine of pi over 4? Rad 2 over 2. So what's cotangent of pi over 4? Something divided by itself. 1. Okay, so here's the difference with cotangent. Cotangent, one difference is the walls are shifted by 90 degrees. Which again, makes sense. Tangent is negative pi over 2, pi over 2. Cotangent is shifted by 90 degrees. Also, it starts positive and then goes negative. So it's going to look the same, it's just going to be like a reflection, yes? Okay, that's pretty good. I like that. It's a little messy in the middle, but just make your, there you go, see? Make it big. Make your dots big, everything's better. So do you see how that's a reflection of the tangent, but it's basically the same shape? Okay. So then you do all the same shit we just did a minute ago with tangent. You get the new period, if I give you a shifted one, are you guys with me? All the same steps apply. I just have to remember this is what cotangent wants to be. So when I do my steps, there's a wall, and then it's maximum 0, max and min, I'm sorry, not really, but it's amplitude number 0, amplitude number on the negative side, fill it in, yes? So when you do your beginning and end, and when you do your step size, you know exactly where those things are going to happen. How we all feel. You want to do an example? Yes, okay. what did I do before? Okay, let's do something different. Yeah, this is nice and freaky. Let's do this. No idea what's going to happen. So what do we see first? Yeah, the quote unquote amplitude. It's 5. And again, I call it that because it doesn't really tell me the highest point it goes to, but it does tell me where I get to, and it's in the same place that amplitude was in for sine and cosine. So I call it quote unquote amplitude. If I factor the inside, what do I take out?
Pi over 3.
Now, here's what's going to happen. We took a pi out, didn't we?
Yeah.
We also divided by 1/3. What's dividing by 1/3? Multiplying by 3. So when I took the pi out, I had a 1, and then I multiplied by 3. If you check yourself, what's pi over 3 times 3? The 3's cancel, and I get a pi. Hey, you get a pi, you get a pi. Nobody gets a pi, actually. I didn't bring this. Sorry. So then I can get several things from this. Let's just get the phase shift out the way. What's the phase shift? -3. So 3 to the left. Okay. What's K? Pi over 3. So how do I get my new period?
Pi divided by pi over 3.
Sure. So whatever the K is, I take what the period was and divide it. Because whatever that number was in front of the X, that's the one that stretched it or compressed it. That's what we knew from before. Same thing happens now, I just call that the period, because that's what's changing. So new period is original period divided by K, which is pi times 3 over pi, which is 3. Where does cotangent start again, normally? When the inside is 0. So actually, this is, the beginning and end here is optional again because it starts at 0, but if we do it, the beginning would start when the inside is 0, and it would end when the inside is pi. So if I subtract pi, multiply by 3 over pi, I get -3. And if I subtract pi, I get 0, so I get x is 0. So it begins at -3 and it ends at 0. Why is that good? What does that jive with? How long did it take it to go through a cycle? 3. And what was that period?
3.
Yes, good, thank God. Because that's what period means. How long does it take for it to go through a cycle? Oh, I forgot the step size. Poor little step size. What's the step size? We always take how many steps? We always take 4 steps, so I take how far I gotta go, divided by 4. Yes. Yes. So I'm gonna begin at -3. Everything's basically happening on the negative side. I'm gonna call this negative, you could do it, Jeff, can you? -12 force, because I wanna step by 3 forces. Is everybody with me? I wanna start at -3. But let me make that become something over 4 so my steps match with it. We've done that before. If I add 3 fourths, what do I get? 9 fourths, add 3 fourths again, add 3 fourths again. Oh shit, this is, I didn't really plan this out well. Add 3 fourths again, big step. Oh well, too bad for me. Where are my walls? Yeah, they're always at the first and last position, yes. They kind of box us in. And then I've got What does cotangent do? I know it's 5 now, so I gotta go to 5.
Negative 9 over 4 is 5.
So cotangent starts at the wall, it starts high, goes to 0, goes low. And then you draw in, make this big. Oh my God, that's the worst one yet. That's bad. Look away, kids. But that would be acceptable if you did that. My last step was so big it got weird at the end. So I might be good idea to not put the y-axis in until you stepped over it for it. Okay. Now, we've done a lot of stuff with sine and cosine. You can see how this is very much related. The graph looks very different, but the step size idea is the same. You have to memorize, if it's sine, cosine, what it does at the various steps. If it's tangent, cotangent, what it does at the various steps. How do I graph secant? What do I draw first if I give you a secant question? What is secant related to? Cosine.
Should be shifted.
So if I, what do you mean? No. If I ask you to graph secant, I first graph cosine,
Right.
yes? And then holy crap. My poor graph. And then I draw the cups up top, yes? And the cups down below. Now I should have made my cosine graph dotted, but oh well. Same thing for cosecant. I graph this, I pretend like it was a sine question. I graph that, and then I put my cups on the top and bottom. Yes. Was everybody here when I was showing Desmos? Did we get that over? Okay. I appreciate you guys. By the time I get to you in the day, I feel like I've done so much. So you have to excuse me. I'm always a little bit wiped out. Okay. So get in there, try those out, come with questions, right? Try those out. I can't remember how the book, you can always keep that worksheet we did, the worksheets we've done, so that you remember the questions, amplitude, steps, new period, step size, spatial, all that kind of stuff, yes? So when I ask you to do one of these on a quiz or a test, I'm going to ask you, find the answer, find blah, 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 blah. I'm not just going to say, graph this, I'm going to remind you all the parts that go into it. You just have to know how to find them. That's all. Okay. So for the idea we're going to get into for today, why does it make sense what we're about to do? What we're about to do. So when we have learned new functions, we learn like exponentials.
Right.
What's one of the first things we do when we learn a new function? Graph it. Another thing we do is, how does it work? What do I do? How do I solve equations with it? But to solve equations with it, what do I have to find? When we learned e to the x, what was the next major function we learned? Or when we learned 2 to the x, 3 to the x? You guys remember we graphed the function before we even knew what it was? And you're all like, dude, I don't remember what you said 10 minutes ago. We learned exponentials, and then we graphed the inverse, and then we gave it a name, or we actually didn't give it a name. We just used the name that crazy people in the past gave it, right? The log. So not surprisingly, we've got 6 brand new functions, yes, that we've been working with, all the trig functions. Well, every single one of them has to have an inverse, or we want them to have an inverse. Let me say it like this, because then I can solve equations with them in it. What's the only reason I can solve the cube root of x equals 2 is because I know how to cube things. And cubing is the inverse of cube rooting, so I can solve that equation, yes? So we're kind of working in the direction of eventually solving trig equations. What is the immediate problem? Can somebody help me out? Can somebody who maybe doesn't normally do it, this shouldn't be that big of an S, because we graphed it, there's one sitting right there. Can somebody come up to the board and just give me a sine graph on either one of those graphs? Can anybody just come? You don't even have to put a scale. But dear God, put stuff in kind of the right place. Yeah, sure, come on up, Trent. And then somebody else is gonna do. I'm gonna get 3 more volunteers.
No numbers needed?
No numbers needed. Just put a sign graph up there. And go backwards too. That's pretty good right there. The little arrow. You're good. No, go backwards for a bit.
Oh.
Cool. All right, put an arrow. Okay. Now, can somebody else come up and I want you to do one of 2 things. I need somebody to draft cosine, or I need somebody to identify positions on this. Thank you. Yeah, come on. I appreciate that. So do either one of those 2 things. Okay. Oh no, I'm sorry. Not graph the cosecant, but
Oh, okay.
identify what this place is.
Oh, okay, that's what you're alright.
Or you can graph cosine. Yeah, now go the other way a little bit. Doesn't have to be perfect. I like the little butt up there. It's good. Okay. Look at it. It's got a little butt.
It's like a mustache.
Yes. Sorry. There's a graph called a cardioid graph that basically looks like that. So students call it the butt graph. So it looks like that. Now, can somebody come up? I will help you. We will all help you. Can somebody try to identify the major locations? Somebody who hasn't come up yet. Right, I'll give you an example. You got what I'm saying, Ron? Okay. Pick either one, either graph. You can give me some locations. Yeah. Now go backwards a little bit. Go to the negatives. There you go. One more step, yeah. Kick ass. Thanks, Ron. Anybody else want to do cosine? I want to play your game, Jeff. I'm on to you. Alright. You guys tell me, what's this?
0.
And what's this?
Half.
Yeah. This will be pi over 2. This is
Higher
pi, good. This is
Negative half.
negative pi over 2. This is negative pi, good. Alright. And I'm not gonna say shit about your scale, because did you see my last scale? Sorry. Right. I didn't even ask for it, I just said, Russ, you're beautiful, it's perfect. Now, can somebody immediately identify the issue with trying to find an inverse function for either one of these?
We don't know.
There is, are they both functions? Why are they both functions?
Because there is only one input.
They pass the
At one positive.
They pass the
Vertical line.
vertical line test. What is required for an inverse to exist? They must pass the horizontal line test. Do they pass the horizontal line test? What does it mean to pass the horizontal line test?
We can only intersect on one point.
Yes. Any imagined horizontal line, any of them have to go through at most once. And there is a horizontal line that goes through an infinite number of times. That's a failed test, yes? You with me? Walk the line, don't come off the line. You just came off the line 80 times. You're drunk, yeah, yes? So we've done this kind of thing before. I can't remember how deep we got into it. But do you all agree that the square root of x is, in a lot of ways, the opposite of x squared? Like you would even hazard to say that it's the inverse. But why is it not really the inverse? Because x squared is this. Does that pass the horizontal line test? Hell no! So how the hell did we make an inverse function when this says an inverse does not exist? Does anyone remember what we had to do? You can remember how detailed we got with this.
Cut off.
Yes! chop this off. Does that pass the horizontal line test now?
Yep.
And that is why square roots can't handle negative inputs and they can't be negative outputs. Because we lost half the graph. We lost information. So in order to make an inverse exist, we had to give up on some information. You guys see that?
Maybe
You guys see that?
give up on the positive.
So over here, I need to do something. I need to chop it, but I want to chop it in a way
No.
that I don't lose all the outputs. I have to represent all the outputs. But it's got to pass a horizontal line test.
Yeah.
So if I look at the sign, obviously, for example, I wouldn't chop it 0 and pi because this piece does not pass a horizontal line test. Also, did I get any negative outputs? Does anyone see where I want to chop this so I have negative outputs, positive outputs, and it passes the horizontal line test?
0.5.
Well, if I go 0 to pi over 2, I do agree with you. Now, what did you just say at the end there? If you go to 0 to pi over 2, it does pass a horizontal line test, but do I get all the possible outputs?
You get negative half.
If I chop it right here, and I chop it right here, that's not an asymptote, by the way. That's me chopping. Yes?
Yep.
I got the butcher knife. Here's what I tried. And this arm comes off. All right, Jeff, shut up. I've watched too many freaking horror movies. Okay.
Yeah.
Is the result, is what's left, does that pass the horizontal line test?
Yep.
So now we can create an inverse. That inverse is not going to be able to do everything for me. Same way square root can't give me negative answers because of what went into creating it, yes? Does everybody kind of get a feel for what I'm saying? So we now can have an inverse sign. And I would represent it. So this is sine, and the restricted domain. Oh, let me move this to the board here. Yeah. Because these poor guys at home, I didn't want to necessarily record any of you guys that could get into weird places. Let's see, blah, 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 blah. See, this is what happened, everybody at home. This is the results of that. Okay, so if I take my sine that we've chopped, beep up, beep up, yep, yep. Okay, there it is. That was very weird. That's just that one little piece. What is the restricted domain?
Greater than or equal to.
That's weird, Jeff. Restricted. It's from negative pi over 2 up to pi over 2, yes? And what is the range? It's still, what's the range?
Negative.
Yeah, the outputs go from -1 to 1. So it still covers all the possible outputs. So what do I want in inverse? That's right. I kind of did this in a different order. That's okay, Jeff. What do I want an inverse function to do? What do I normally plug into a trig function? Can I plug a point in there? Can I plug the length of a dog's nails in there? Can I plug? What do I physically plug into a trig function? What's the only thing that makes sense to put in there? Give me an example question I could ask you that you have to have memorized. I could ask you the sine of, okay, or I could ask you the sine of pi over, okay, what are those? What is 30 degrees? What is pi over 2? Those are angles, thank you. Okay, so what's the only thing we're allowed to plug into a trig function is an angle, yes? So the input is an angle, and what's the output? Very often it's a ratio, but it's definitely a number, yes? Are you guys with me? So like sine of pi over 2 is 1. What's the sine of pi over 6? 32. That's what it is. Well, what's the sine of pi over 6? 1/2. And it could, of course, it could be putting you on the spot. But does everybody have a way to think about that question? If I say sine pi over 6, do you have a way to think about it? Or does anyone just have it straight memorized?
I just think about it for a second.
Sine of pi over 6, sine likes y. Pi over 6 is closer to x. It should be the smaller output, 1/2. That's exactly what I think. You don't have to think the way I do. I'm just saying that's an example of how I do it. What are we doing over here? So, what is the input for an inverse sign? And what is the output? The number is the input. The output is the angle. So what does an inverse function do? It switches x and y, yes?
Yeah.
Is everybody with me? If I ask, oh, go ahead. Okay. If I ask you, what is the square root of 49? What do you think? Some of you guys might have that kind of memorized in a way, right? Huh? No. We just got done earlier talking about the square root can't, but now you're answering. 7. What do you think to yourself though? If I ask you by hand, calculate what the square root of what, Jeff?
I don't know, Jeff.
What's the square root of 625? How would you try to do that if I said you fail if you don't do it? First step is after class you go report me, and that would be the appropriate thing to do. Yes. But if you did have to do that, what are you thinking about? How do you do a square root? Oh, okay. But what are you thinking broader than that? That's specific to the number I gave you. You're thinking, what do I multiply by itself to make that? Because you're thinking in terms of the inverse of it, yes? Okay, so if I ask you, what is the inverse sine of 1/2? You're thinking to yourself, what angle would I take the sine of to make 1/2? When I ask you what's the square root of 49, you say, what number would I square? Oh, what number would I apply the opposite function to get that? Okay, inverse sine of 1/2. What angle would I take the sine of to get 1/2? And what angle would I take the sine of?
30.
Yes, closer to the x-axis. Give it to me in radians, though.
I over 6.
Yes. If you have your values memorized, the inverse trig questions are fundamentally just, do you remember this stuff? It's just kind of backwards. So it's like if I ask you what's the sine of pi over 3, you tell me it's rad 3 over 2. If I said what's the inverse sine of rad 3 over 2, you go, what would make the answer? It's pi over 3. Okay. It's the same thing, just backwards. So if you know it, now it's asking you, do you know it backwards?
Right.
Here's the twist. What is the domain of the inverse sine? Now, some of you guys might feel like I haven't given you enough information, but remind me, what's an inverse function do? How do I graph it or find it algebraically? I do the same thing.
You just change the axis.
Yes, whatever the points are, I just switch the x's and the y's, yes? Remind me, what is the domain?
It is
For any function, what's the domain?
negative pi over 2.
No. For any function, what's the definition of the domain? It's all of the... No, what's the domain, the definition? What's the domain of 1 over x minus 1? All numbers except? 1, why? 1 makes it freak out. So what is the domain? It's a collection of all inputs that work. That's what it, and so it's a collection of x's, yes?
Yes.
And what's the range? A collection of y's, yes? What does an inverse function do with all the x's and y's? Changes them. So if the original function has a domain, I put an R for restricted, has a domain of this, what's our range for inverse sine? This guy's domain is this. What's the range of ours?
It's
That. Because what does an inverse function do? It switches all the x's and y's.
Yes.
If a domain is all the x's and range is all the y's, what's an inverse function do? Switches the domain and range.
Yep.
It's just on a higher level. So the range of this is negative pi over 2 to pi over 2. And the domain would be negative 1 to 1. And that makes sense. What would you say? Well, let's do this first. What's the inverse sign of, you could do it, Jeff, of 1? What are you asking yourself to do that question? Don't tell me the answer. Tell me, what are you thinking to yourself? You're thinking to yourself, good God, should have stayed in bed. So watch this later.
Sine of what equals?
Yes, what angle do I take the sine of to get 1?
Do you prefer we enter radians?
Yes. That's what I prefer is what you do. No. Just do radians, yeah. So what is it? What do I take the sine of to get 1? Pi over 2, because that's where it likes it the most, on the y-axis, yes? Does that answer fall into the acceptable range? Yeah.
Yep.
Yay. So here's where things get trippy. What is the inverse sine of negative 1/2? So here's the question. What quadrants can my answer live in? Let me show you this again. Yes, because the answers for my inverse sine live between negative pi over 2 to pi over 2. Negative pi over 2 is here, pi over 2 is there, yes? If it's a positive input, I'm in the first quadrant. If it's a negative input, I'm in the fourth quadrant. What angle makes sine 1/2? Forget about the negative. What angle makes sine 1/2? 5 over 6, 30 degrees. Close to the x-axis, sine hates it there, yes? So I just make it negative pi over 6. Why do I have to do that? Because the way we restricted sine for this to even exist only allows me to live in so many quadrants. So inverse sine can never give me an answer in the second or third quadrant. There will be situations where that is supposed to be the answer, and then what they give me is a referencing. I put it into the quadrant, and we're going to see that later. Let's not do that yet, John. Okay, how do you guys feel? For the most part, this is just, do you know your values? Yes. Right? Not your general values of life, but like, do you know cosine of pi over 6? Because now this is just taking that and turning it around. If I give you the output, can you figure out what input makes that happen? What angle makes that happen? The only twist is, if it's negative, it's the fourth quadrant. You got to think negative angle, yes? If you really think about it, that kicks so much ass. If that is pi over 6, that's negative pi over 6. You can't beat that shit if you think about it. If that's pi over 6, that's negative pi over 6. So that's straightforward.
Yep.
Now, what about cosine? Let's do it again. Does cosine, I'm sorry, I just love this little button. Does cosine by itself pass the horizontal line test? No. Do I want to cut it like here? No, because it still wouldn't, yes? Does anyone see a way to cut this?
0 to half pi.
Not quite, because if I only go from 0 to here, I'm only getting the positive possible outputs, yes?
0 to pi.
If I go 0 to pi, now I'm getting all the possible. I'm just going to make this go a little deeper this way. Otherwise, I'm going to drown here. Yeah. Now I'm getting all the possible outputs from negative 1 to 1. So I have to chop it so it passes the horizontal line test after I chop it. But I don't want to lose possible outputs because I want this to be able to go backwards. And if I chop it to here, I won't be able to answer any negative questions. I would have chopped off too much of this poor guy. So, for the people at home, if I take cosine, take cosine, yeah, wow, and I go, so this is, doesn't matter, Jeff, this is 0, and this is pi. If I just chop it there, so I just focus on die, from 0 to pi, that passes the horizontal line test. It includes all the possible outputs. Okay, so now, this guy's domain, I restricted it to be 0 to pi, and of course, what's the range?
1 to
Negative 1 to 1. So for inverse cosine, this is cosine, by the way. What will its domain be? No. What will its domain be? Yeah, all the x's and y's switch, so it's going to be negative 1 to 1, and its range is going to be 0 to pi. Now, the really nice thing about inverse cosine, what is the biggest angle that can exist in a triangle? Almost 180, yes? You can have a 179.999 degree angle, and then the other two are very, very, very tiny, yes?
Yep.
And what is the smallest angle you can have in a triangle? Almost
Almost
0.
0.
So, inverse cosine allows for angles from 0 to pi, like 0 to 180 degrees. Later this semester, we'll see why that's nice. That actually makes a thing we're going to do. Well, actually, it's very soon for us. We'll see. So again, the same idea, except now, if I give you a negative answer, like a negative input, what quadrants am I allowed to be in? From 0 to pi is what quadrants?
1 and 2.
From 0 to pi, yes, 1 and 2, yes? You guys with me? Why does that make sense? What's cosine, what's the sign of cosine in the first quadrant? SIGN. Is it positive or negative? Positive. What about in the second quadrant? What's the value of x in the second quadrant? And cosine likes x, so cosine is negative in the second quadrant, yes?
Yes.
So it makes sense that if I capture all my possible outputs, I gotta go from 0 to pi. I catch all my positive, all my negative. Okay. So what angle makes cosine 1/2? To make cosine small, I have to be far away from what axis? What is cosine like? What is cosine like? X or y? Cosine likes x. To make the output of cosine small, I have to be far away from the x-axis, close to the y-axis. So what angle is that? No, what angle is that?
60.
Which is pi over 3. Good. 3 times 60 is 180. Yes? 5 or 6, 5 or 3. But here's the trick. What quadrant do I have to be in, considering I can only be in the first and second? What quadrant out of those two would allow cosine to be negative? Second. So I know I have a reference angle of pi over 3. So what angle are we actually talking about?
More than 1.
If I'm 1/3 of a pi away from a full pi?
2/3.
Yes. So that's where cosine kind of sucks a little bit. It's always going to have a positive answer, but it's got to be in the first quadrant or the second quadrant. So if I'm doing inverse cosine with a negative number, I'm going to be in the second quadrant. I actually have to think reference angle. So you get the actual angle that's in the second quadrant. If you say your answer here is pi over 3, that can't be right, because then it wouldn't be negative 1/2. It would be positive 1/2. It can't be right. Maybe. Do you guys understand why there's a trade-off here, or why we have to kind of like dance around this a little bit? Because in order for these inverse functions to exist in the first place, I had to chop stuff off. I had to lose information. Okay. Now, can somebody help me notice something? Because I'm not observant. Every time we've done an inverse sine, or an inverse cosine, whatever, what's the answer always been physically? I know I made a big deal. In fact, it's right there. What's the answer always been? An angle, yes? So let me truncate that. If I gave you, even this, an inverse trig function of some number, what does this represent physically? An angle. Good. Okay. I really want this. I love you guys so much. The same way I teach that logarithms are powers, and then made a lot of other stuff make sense. Inverse trig functions are angles. They are. Because what would the output to this be? An angle. So what does this represent? An angle. What triangle does this live in then, for example? It's an angle, so if I call this theta, it lives in a triangle. Do we know anything about the triangle? We do. It's the triangle where the tangent of the angle is what? I told you. So normally for a tangent, I give you the angle and you figure out the ratio. Yes? Rad 3 over 3 or whatever, you with me? This time, I told you the ratio.
So that's 7.
Yes, the angle lives in a right triangle. It's got to be the angle where the tangent is this. So therefore, where's 7?
7 into 12.
And where's 5?
X.
Yeah. So here, before I do anything with that, can you guys do this? Can you guys draw a triangle that goes with this? The representative triangle for this. Don't say anything. Draw just what you know, just what you see. Make that into a triangle with the stuff in the right place. Don't say anything. Except the question. If you have a question, you can say that. I am going to let you work on a handout here in a minute, but I got to get you to a certain point before you can do that. So where do you see what I'm asking? What information did I give you? Normally if I ask you like, what's the sine of pi over 3, I've given you that the angle is pi over 3. This is the inverse side, so now I've given you the ratio of the y side and the hypotenuse. So right there, if I ever give you an inverse trig with a ratio inside, or a number, you can draw the representative triangle. Where's 4 go?
4.
Because I want to know. And where's 11 go?
Hypotenuse.
Yes. And then this is the angle that this is representing. Do you guys see that?
Yeah.
So when I ask you a sine question, I'm giving you an angle information. When I ask you an inverse sine question, I'm giving you a ratio. And then you can draw the damn triangle. Now ooh, look at us go. So what can I do with this shit, Jeff? Well, if I ask you, what is the cotangent of the inverse sine of 4/11ths? Do you see how to answer that question now? Do I have a triangle that represents the inside? Can I find the cotangent of that angle?
Yeah.
What am I missing to get the cotangent?
Yeah.
Do you guys, I need to stop for a minute. I really want you guys with me. Inverse trig represents angles. Those angles live in a triangle that match with what's inside. That's the ratio, yes? I can always draw a representative triangle if I'm given an inverse trig, because it represents an angle that lives in a triangle under the sun. So this should feel like an old problem. This is one of the first problems we did with trig, but wrapped up in the brand new shit, yes? So let this be actually nice. This looks horrendous. If I would have just written this down and said, how do you guys feel about this? You would have went, don't do that. Do I have a vote? But do you see how this is nothing that big? I actually tell you the ratio, I tell you what sides they go on, and then I ask you, okay, well, how do I get that last side? What do I use?
It's square root of 105.
Yeah, I use old Greek dude. So this would be 16 plus x squared equals 121. So x squared equals 105. So x is square root of 105, 11. So what is the cotangent?
So tangent is
Cotangent, yeah.
y over x. So
No, careful, that's tangent. I want cotangent.
yeah, so that's tangent is normally y over x.
Oh, I'm sorry. Tangent's normally y over x. So this would be root 105 over 4.
Yeah.
Yes? Do you see how there's very much familiar work in the middle of this? all of that we just did is very familiar. You guys, we've been doing that for a while. But it's wrapped up in this kind of brand new way of giving you information.
Yeah.
Okay, let's see if this makes sense. So try to work on some of this by yourself first. I'll give you stuff to talk about when you get the groups. It's not cold. My printer must have run out. I hate it. I'll be right. So at the top, I just put, I don't know if this is the domain and the range for each of these. Now, inverse tangent I didn't really talk much about, which is, oh well, these things happen. But real quick, I should talk about inverse tangent. So before you jump into that, let's talk about inverse tangent. Here's tangent, yes? Basically, yes? Holy shit, I really zoomed in. If I do, now is this invertible already? If I just draw this one cycle, is this one-to-one? Does it pass the horizontal line test?
Yeah.
Totally. As long as I don't draw the infinite copies, if I just draw this one thing, it's already invertible. So what is the domain that I'm going to use? No. Did I use all real numbers? If I use all real numbers, I'll have all these copies. I don't want that because then it won't pass the horizontal line test. So what did I restrict the domain to be? Yeah. Negative pi over 2 to pi over 2. I can't include them because they are asymptotes, yes?
Yeah.
So if I restrict my domain to go from here to here, that is invertible. It passes the horizontal line test. And the range, of course, what's the range? Huh? Yes. Negative infinity to infinity. So the inverse tangent looks neat. The inverse tangent looks like this. If I just flip this, yeah, it's going to look like this. So it goes from negative pi over 2 to pi over 2 for alpha. So here's the range for the inverse tangent, negative pi over 2 to pi over 2, which is the same thing as sine, which makes sense because what's on top of tangent is sine. So tangent goes like sine. So give these a try. Give these a try. I'll put you in the groups here in a minute. Kind of try to look at all the problems, see how you feel about all of them, especially those last two, but maybe save those for you. let's see. We'll do by twos, I think. Let's see. Layla, can you work with Charlotte right there? Okay. Trent, can you work with Christian? And Ethan, can you and Ronnie work together? I thought I did even number people. Oh, I lost somebody. Who is that? Oh, that's right. Can you guys over here, Christian, Dylan, and then as soon as Giant gets back, she's back here with that pink water bottle. She said that. You guys will work together.
Oh, okay.
Let me know, or let me or Christine know if you
I
need
can
help.
get the cotangent one. I think. Yeah. Where do you get lost?
Oh, I think this one is different.
Yeah.
I was thinking the same thing when I was passing it out.
Or this one, I was just imagining how this point is kind of went over that one. We skipped over to Sean, so he did this one. So that's why he clicked in the last one. So, because we know
Oh yeah, it's the law of science.
the positive version is pi over 3. If we take that like that, all we're doing is making it negative, so there's like the extra 60 degrees, and we use negative. So it's in radians,
Oh.
pi over 3.
It's not a big deal. It's just when you see this question,
It takes
normally for sine,
I think I might need to review the unit circle.
what
So I
angle
can remember.
makes the sine 1 half? So this is related to the values you have to memorize.
Alright,
Yeah.
so what about this one?
Radius. Thank you.
Okay,
So you gotta think about it backwards, just like any inverse function, you gotta think about it backwards.
because it's weird. I'm not sure where to go from there. But these ones are very easy.
So you know that cosine is 2
Negative 1. Oh, yeah.
So you know where 2 goes.
We just know tangent is can have it.
So it's still the same definitions. Cosine is still x over cos. But it's like I'm telling you the ratio.
I don't know how to explain
And
how
you
it's
gotta
the
think
answer.
about
That's
it.
okay, I see where you're getting it from. I just don't know how to actually do it.
I just somewhat, have it somewhat memorized how to tell where is something.
Well,
We have pi, and then the negative 1 piece is going to be half the pi,
Sine
so you have
is
3 pi
actually
each.
easier.
That's how I got that.
It really was like 0,
Is that
first
true?
one.
I'll have to question myself.
So whatever you normally would do, if it's negative, you just make it negative. Cosine
The
does
tangent
0
is,
So if it's a negative answer, then you actually are speaking about a reference angle. What you know the reference angle now, just figure out the actual angle. And do that backwards. So like what angle makes cosine? What's that?
because
5 or 6.
negative
So that's the reference angle now in the second quadrant. Because I know about
it has those two quadrants.
inverse only gives answers.
There's the second and the fourth.
5 or 6
But because it's limited,
an angle that puts things in second
equal
quadrant.
1 and negative 1, so
5 or
we
6
know
here.
this is going to equal.
This is pi. Yes. So go to degrees. How far short am I?
Yeah, this is very early.
1/6 of the class short.
So,
There's a language in the
5.
yeah. These make more sense because you do the triangle.
That was easy to kind of understand and got into it.
So, this is a small and wave moment, but you skip to the next one, and maybe you understand that. And then you
Sine
ask
is also
questions.
these kind of constants. It's
Yeah.
just whatever would be just
This
basic.
is,
So,
Tangent
would it be the same
of-
thing for tangent, or would this be?
do you want us to figure that out?
Yeah.
Yeah.
This first or fourth one.
But
So it's
you
the same
said-
thing. Whatever it If it is negative.
Like pi over 6 minus pi over 6 would be.
Yeah, since pi over 4 would make tangent 1, negative pi over 4 would make tangent 2. And you guys understand that?
Just, yeah.
There's an angle in the second one that would make tangent.
I kind of,
So 3 pi.
cosine is the y over the hypotenuse, and then in trying to find
Because of the way we have it.
you can easily quickly find the x, and then the tangent is the y over the x.
Oh, right.
Am I
Sorry.
supposed to solve this?
Values for the inverse cosine.
Yeah.
Leading us on that we should already know how to do that.
Giants coming.
2 over square root of 29. I'm gonna say maybe
Set you up. That was so easy. Oh, man.
cross that bridge when we get to it.
That was all by yourself. I'm sorry.
Right, cotangent.
Just doing it like first in degrees and then comparing. Yeah, that works too. Yeah, it takes a minute to kind of incorporate radius.
No, you have to.
This is the x over the y. Right?
Yeah, I love this. So for one thing, it should be pi over 3. For cosine,
This
it
is
should
gonna
be
be
close to
4,
the x-axis.
7,
So if that was negative, wasn't there?
49.
If that wasn't negative, how do you make cosine run 3 on 2? Cosine is x. So cosine is big when it's close to x. Which angle is close to the x-axis? 5 or 6.
Then secant.
So you divide by big
Yeah,
X.
just get to
5 or 6 is close to 0.
Reverse.
I mean,
Since it's a negative number,
it'll take time to
the
do.
answer's not pi over 6.
But if you do it this
Pi over 6 is the
Let's go
reference
back.
in the
So
second
we
quadrant.
have
So if this is the second quadrant and this is pi over 6, what's this?
cosine is y over
Yeah.
2.
What's this?
Look,
What's this? This is pi.
Cosine
And this
is
is how much?
to write our answer.
the
Pi over 6. Alright. So I'm pi over 6. I'm 1/6 of pi short of the whole line. So
Yeah, cosine likes x. So
Pi
it
over 6.
would be 7 over the. There's
So on these specific problems, inverse cosine prime
no,
is
secant.
sine, inverse sine gets x, because
Hypotenuse.
if you would normally be pi over 4, it's negative, you make it negative pi over 4. That makes sense. Inverse cosine is, if it's only pi over 4, that's now a reference angle, so now it's not a 3 pi over 4. Because of the quadrants I have to live in, because of the way we have to chop it.
Everything just likes to leave my mind when it comes to working with other people. It happens.
Oh, I guess you could stop.
Seven pi over 4.
Yeah, that won't be the answer though.
It won't.
No?
For what?
It won't be the answer because inverse tangent has to live between negative pi over 2 pi over 2. 7 pi over 4 is way out of
So it's
there.
gonna be negative pi over.
Yep, negative pi over 4. Now, we know there's a coterminal angle, but
Yeah.
officially, inverse tangent can only give me these answers.
Right.
Okay. So guys, I'm sorry, back there. When I see this, I think this. Holy shit, I wrote over the next problem, too bad. When I see this, I think this. What angle makes sine 1/2? What'd you guys get? Nobody wants to talk to me, huh?
5 or 6.
Yeah, I want sine to be small, so I want it to be far away from where it likes it. I'm gonna put it close to the x-axis. 5 or 6. I'm done because it's positive, so I can be in the first quadrant. Thank the gods. Now let's do this in 2 steps.
This one's
What angle makes cosine rad 3 over 2, and then I'll worry about the fact that it's negative. What angle makes cosine rad 3 over 2?
pi over 3.
Yes. No. Pi over
Or
6. Again. Ha ha ha. When sine is small, cosine's big. Cosine likes the x-axis. It's bigger when it's closer to the x-axis.
Mm-hmm.
Now, here's the problem. Inverse cosine's answers live in the first or second quadrant. So where's the only place that I could be to make this negative? Second quadrant, because the first quadrant makes the answers positive, yes? So I know I'm in the second quadrant, and I know my reference angle is pi over 6. So what's my actual angle? I stopped 1/6 of a pi short of a full pi. So how did I get there? 5 pi over 6. If there's only 1/6 of a pi left, somebody ate 5/6 of that damn pie. So 5 pi over 6 is my answer.
Greedy person.
Totally. Some kind of asshole. Later, we're going to learn that cosine, I say that cosine is an asshole, and we'll see why. Right now, he's actually pretty chill. Not too bad. Well, he's a little bit of an asshole here. So that still works. I love it. This one, tangent goes like sine. I've said that before. So in this case, it helps because if you remember, sine goes from negative pi over 2 to pi over 2. Tangent inverse goes from negative pi over 2 to pi over 2. Same way. The answer is negative, so I know I have to be in what quadrant then?
Fourth.
For the inverse tangent, it's got to be fourth quadrant. You guys all know that tangent has a negative answer in the second quadrant, but that doesn't matter because inverse tangent has to live between these two. That's the answer it's going to give me all the time. So to make tangent 1 is pi over... What angle makes tangent 1?
Pi over 3. Wait. Pi over 6. No.
Okay.
Pi over 4.
Not pi over 1. I'm not done drawing because I was waiting for the answer.
Pi over 4.
Maybe. We'll see. What's tangent again? What two trig functions divided? Tangent is what over what? So what two trig functions? Sine over cosine. Y over x, sine likes y, cosine is x, sine over cosine. When is tangent going to be 1 then? When sine and cosine are? Since it's sine divided by cosine, what's the only way to get 1? If sine and cosine are the same. If I divide two numbers and get 1, the numbers must have been the same. When are sine and cosine the same? 5 and 4.
That's new stuff.
But it's negative.
So that brings fuzzy.
So instead of going pi over 4, I just go back pi over 4. Then I'm in the fourth quadrant. I'm good.
Right.
Okay, I can tell you guys, this is the best thing the whole semester, this is the best. Like, I like this, Jeff. Give me more of this. Okay. Again, the better you have memorized tangent of pi over 4, cosine of pi over 6, the easier this is. The tricky part to me is you have to kind of like figure out how to remember this. Cosine 0 to pi, sine and tangent are negative pi over 2 to pi over 2. This one, okay, listen. This, do you guys appreciate that I gave you that one? You're like, you asshole. You didn't even talk about cosecant. You butthead. So, if the cosecant, if an angle makes the cosecant rad 2,
Yeah.
what does that make sine? For example,
Sine would be
1 over rad 2.
1 over.
Right, I need you guys to really be with me. If there's an angle that makes cosecant rad 2, it has to make sine 1 over rad 2, yes?
Yeah.
Because how does sine and cosecant relate? They're inverses, reciprocals. So, I can translate this damn question into a much better question. And why is that much better? Because if I rationalize this, what do I get? You're rad 2 over 2, and that's a very familiar number. What's the inverse sine of rad 2 over 2?
Pi over 6.
No.
No.
Sorry, Trent.
Pi over 4.
You're so confident, and you're like, damn it! You said that so confidently.
My head is still fuzzy on this.
I understand.
topic.
All right.
Takes time.
All right, real quick. To make a number bigger, I divide by less.
It's
You guys agree? So I have 0. This is pi over 6, because this is pi divided by a lot. That's pi over 4, because it's pi divided by a little less. So the answer is bigger.
Yeah.
That's pi over 3, because that's pi divided by even less. And that's pi over 2, because that's pi divided by even less. Do you guys see? So I know rad 2 over 2 is where in the middle. Because big sine is rad 3 over 2 and small sine is 1/2. Rad 2 over 2 is in the middle. And what's right in the middle of 0 and 90? 0 and pi over 2? Pi over 4. So pi over 4 is what makes sine and cosine both rad 2 over 2. Okay. So if you're still a little fuzzy about just your straight up cosine of pi over 6, blah, 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 you got even more reason to firm that up. Okay. Whatever you say, Mr. Waller. Okay. Number 2, I think some of you guys did number 2 first, and I love it because once you realize how to read it, when you first look at that, it looks like, what the shit? What the shit do I do? You plugged an inverse cosine into a tangent. What am I supposed to do with that? But when you realize inverse cosine is an angle, and I can draw the triangle it lives in,
Yes.
this becomes really silly. This becomes one of the first questions we talked about. How do I draw the triangle? Well, Jeff, it's got 3. Shut up. What do I put the 2? Where do I put that? Where?
Why?
Because I want to know. Yes, because cosine likes x. So if I put the angle in the base,
Right.
cosine is 2/5. And so it's telling me the base is 2. What's 5?
Hypotenuse.
Because it told me cosine. So I know the ratio relates to x over hypotenuse, yes? And now it's asking me for the tangent. Yes? So what am I missing to figure out the tangent? The y side, yes? So that would be 25 minus 4 is 21. That's the square root of 21. Is that cool? So what's the tangent?
Square root 21 over 2.
Done. Done. So each one of those works the exact same way, even that last weird little dude. I love that last weird little dude. How do I draw this triangle? There you go. You did it, Jeff. Show. Where's 7?
X.
Yes, it's on the base because cotangent is x over
Y.
y. Then this will be 49 plus 16 is 65. Is that cool?
Yep.
You guys all with me? Very quickly, just to show you. 49 plus 16. 49 plus 16 is 50 plus 15.
Yeah.
You can do it in your head quicker, yeah. That's something called compensation. Compensation. It doesn't matter. So what is the secant of this angle then?
Square root 65
Good.
over 7.
Good, because secant is related to cosine. So flip the cosine. Done. Did anybody? Well, I've seen a few of you guys do part C, and you're making the mistake I knew you would make, and that's fine, because you're not a Calc 3 student making that mistake. So the mistake people make on part C is the same as people mistake in Calc 3. And I'll see if Christine agrees, if she's seen people make this mistake, or if she's done this herself. I did this myself as a student. Okay, so what am I talking about? I don't know. So I can draw a triangle because I have an inverse trig.
Mm-hmm.
So I can put the angle it represents in the base. Where would y go?
Y.
Because I want to know. Where would 3 go?
Hypotenuse.
Hypotenuse, because sine is the y side to the hypotenuse. That is y. It just is. Too bad. What do I need to know to answer this question?
X.
The base. It's not good enough to just call it x and say the answer is x over y. I have to know what it is in terms of these other things, what we always do. So then I use old Greek dude.
Yeah.
How do I solve for x?
9 minus y squared.
Now here's the step. Here's the step. Here's where everything goes to shit. If I take the square root, I cannot make that 3 minus y. And here's why. Do you guys agree that the square root of 13, does anyone think the square root of 13 is 5? Let me say it like that.
No.
Huh?
No.
I can't hear you. I'm sorry. No. Is the square root of 13 5?
No.
What's the square root of what is 5?
25?
Okay. So do y'all agree the square root of 13 is not 5?
No.
Does everybody agree with me?
Yeah.
I need to check. 5 times 5 is not 13, yes? But let me show you that it actually is true. You ready?
What?
13 is 4 plus 9. The square root of 4 is 2. The square root of 9 is 3. It's 5. There. Nah. Square root of 13 is 5. All of your knowledge is wrong. No. What mistake did I make? I made a very subtle mistake.
Order of operation.
Yes. Guys, help me out. Is this true? And the answer is no. Is this true?
No.
What did I do wrong? What am I missing? I have to FOIL it out, yes? Now, why do I have to go through extra trouble? What is this? What is xy squared?
XY squared.
No, come on. No. What's xy squared? Come on.
X times
X
Y.
squared, y squared, yes? Why was that so damn easy and this is so freaking hard? This is not true. Because what are exponents based on? What are exponents based on? What operation? What operation are exponents based on? Multiplication, yes? If I said do 19 squared by hand, you would write 19 twice and multiply it, yes?
Yeah.
And this is multiplication, therefore it plays well. It's based on multiplication. If that guy's multiplying, it plays well with it. Based on multiplication, are these multiplying? Shit! It's not going to play well. I've got to do extra shit. Now, what's the square root? Well, how can I rewrite a square root?
The square root times the square root.
No. Have we talked about this yet? Shit. Do you guys know it's a 1/2 power?
Yeah.
Okay. So can I distribute a power? And do you no? Can I? Can I distribute a power?
No.
I can if I want to get to the wrong answer really fast. And if you want to do that, I don't know what your goals are, but so the mistake I made is I distributed the square root to each piece. I am not allowed to do that because square roots are based on multiplication. They're trying to undo
Right.
multiplication. They can't play well with addition. That's a mistake. So the mistake people make here is they say this is 3 minus y. That is a mistake. Huge mistake. I need you to understand. It's an understandable mistake because your brain wants to simplify shit. What have math teachers been telling you your whole damn freaking math life? Simplify. What are you doing? Simplify. Don't tell me 6 over 8. You're like, all right, simplify. Yes, I'll simplify. So then you're like, simplify. No, but you can't do this. You guys with me? This is apparently a really big deal to me. I'm sorry. But this is a very simple mistake. And there's so many little things in mathematics. Maybe, Christine, you don't have to back me up. But once you get to especially like Calc 2, trig sub, for example. Holy shit. You do this everywhere, everything's wrong. Everything is wrong everywhere. Okay. All right, Jeff, Mr. Doom and Gloom. So what do I do with this? Nothing. That's what it is. So help me out then. What is the cotangent of this angle? Don't overthink it.
Cotangent is 9 minus y squared.
Yeah, the square root of 9 minus y squared over y. There, that's all it is. That's what it is. So over here, I just happened to tell you this was 7. If I told you this was x, all this shit would have been exactly the same. I would have just had x running around. So over here, I'm like, I'm tired of making numbers up. That's what, I don't know what number that is. It's y, right? I'm like, I've made so many freaking numbers my whole life. It's just y. So I do the exact same shit. It's exactly what you would have done if I would have said that was 2. Okay, maybe. This is huge for us in this class and for like future. Okay. Now these were a little bit evil, but let me do the first couple steps. I forgot my calculator, so can somebody relate what I've told you in that angle with the trig function? What trig function would relate all of that? Cosine. Cosine of A would be?
7 over 11.
Now, how would you solve this equation? You could do it, Jeff. Can I? How would you solve this equation here? No.
Oh,
Square root.
yeah.
Right? Kill that. I would apply the inverse operation. How would you solve this equation over here?
Multiply by 7.
Apply the inverse operation. Yes? What's the inverse of divided by 7? Multiply by 7. So how do I solve this equation? Apply the inverse operation. Now I've shown you examples like this before when we first talked about inverse functions. What do these do to each other?
Murder each other.
Totally murder each other. So blood, blah, blah, pool. Okay, sorry.
1.
So what's left on this side?
Uno.
Well, no.
No.
What did we just free? A.
Okay.
Do you see in your calculators a cosine inverse button
Mm-hmm.
that's above your cosine button? So you can actually make sure you're in, it doesn't matter. Just plug it in and see what you get. We'll see if you're in degrees or radians. What'd you get?
0.0902314.
Okay, that makes sense. 09, oh, flum, thumb, bum, blah, blah.
Yeah.
Yes, exactly that. Did you get the same thing, or what'd you get?
It's still loading.
It's still thinking?
Yeah, it's still thinking.
Uh-oh. All right. Poor little guy. If you have it in degree mode, you'll get degrees. Obviously, you have it in radian, you can get radians. You guys understand? So we have the ability now that we know inverse functions exist. We can actually solve for the value of an angle if I'm given the side lengths. Yes? Do you understand what I'm saying?
Mm-hmm.
So if I want to know what the angle is between two things, I just have to get the right trig function and then take an inverse of both sides. And then I got the buttons in my calculator. So on this one, what would I set up? What relates to the stuff here? Tangent. And then I would take the inverse tangent and I would throw that in the old calculator. And see what happens. Yes? You guys get that?
Oh. Wait. 50.
Yeah, maybe. Potentially. So that's one of the most immediate applications of inverse trig functions is I can get the angle between things if I get it in a right triangle and I know the side lengths. I can just do the inverse trig. Whatever trig relates what I know to what I want to know. Okay. Just to give you a little preview, we are headed very soon into extending trigonometry into working for non-right triangles. That kind of looks like a right angle, damn it. So if I have a non-right, there we go. That triangle's not right. All the other triangles walk around going, that triangle ain't right. Something wrong with that little triangle. All right. Somehow we're gonna get sine and cosine to cooperate and tell us stuff about a triangle, even if it's not a right triangle. So we're gonna extend the usefulness. We're actually gonna take the Pythagorean theorem, and I'm gonna show you the full form. You don't know the full form of the Pythagorean theorem. You don't know his final form. It's over 9,000. Okay, so we're gonna talk about the final form of Pythagorean theorem, and we're gonna talk about how sine and cosine kind of like act in a non-right triangle. What can they tell us? At the moment, they can't tell us shit, but we're gonna make it so they do. Okay, right? All right, that's enough for today, guys. I don't know when the next quiz is gonna be. I don't think I've announced it, but we've done. What have we done? What have we done? We'll talk about it tomorrow because I haven't really sat down to think about it. Oh, I'm sorry. Did I take that away? Were you talking about something?
So if you just like filled in the blank parts that could make it a right triangle.
Yeah, what we're gonna do is sort of like what you're talking about.
And then you can.
Then I can relate things. Yeah, we're gonna construct. We're gonna analyze this, sort of like what you just said.
Yeah.
To be honest, we're gonna use it with something more like this, because then if I drop this down, I've made two right triangles.
Yeah.
But I can reference everything to the whole triangle that isn't necessarily a right triangle. Yeah. Good.
Yeah.
Yes. Okay. So right above the tangent, so hit the second,
3,900.
and then just do 5 divided by 12. There you go. So you got it in degrees, so 22.6, and if you change it to radians,
Okay.
Good. Yeah.